Hey students, as we talk about clamping forces, one thing that often comes up is how big a force are we talking about? And so the force, of course, that's excellent, that's like Dr. Seuss. The force, of course, depends on the horse that you're using to produce the force. No, it actually depends on the process that you're utilizing. And so we calculate that, and we're going to do that in the next video, but in this video we're going to kind of look at the magnitudes of how big or how small that could be. And some of it's pretty surprising. So starting off with, let's see, let me make myself small. We want to remember that our biggest forces are probably going to come from machining processes. And so we're going to spend a little bit of time on machining processes just because they are very common and also some of what we get. Now remember, as the tool cutting edge moves through the material, it moves through with this thing that we call the cutting speed. That's how fast the cutting edge is moving through. And if you remember way back to 231 and maybe 332, the cutting edge, the cutting speed, is got really funny units in the imperial system. It's surface feet per minute. And so feet per minute is what we're working with there. Also, I want to remind you that there is friction that is happening between the back side of this chip and the front side of this tool. And so that friction is always trying to push the tool up and out of the material. Or if we're holding the tool in place, that friction force is always trying to push the part deeper down into the fixture. And so we will have forces that are both along the path of travel and pushing the part down into the fixture. If you remember way back to 231, there are some weird circumstances where you can get those forces actually trying to lift the part out of the fixture, but they're relatively rare. So if you want to go over all these terms and remember them, that would be great. But anyway, not super important right now. What we're going to do is go on, and I want to remind you again that the forces can be broken up in many ways, because we have really what we have is this resultant force on the cutting tool, or this resultant force that the cutting tool puts on the part. And so we can break that up into a bunch of different ways. One of the ways that we really like to break it up is into the cutting force, so that's along the direction of travel, and then the thrust force, that is what's the element portion of the force that's trying to push the tool up out of the material or trying to push the material down into the fixture. Remember, we can also do it other ways. There is the resultant force right there, and so that is the force that is actually on it, and we can make up lots of different couplets of orthogonal vector pairs that that have this resultant. And so we often use cutting and thrust forces. Remember, we can use the friction force and then the normal force that creates that friction, and then the force along the shear path and what we call the hydrostatic force as well. But we're mostly going to focus on the cutting force here. And so if we look at some graphs, and of course these are just some graphs. There are lots and lots of different graphs that you can get depending on material type and process type and all. But when we're looking at this, what we see is forces on these graphs somewhere between 50 and 250 pounds. And this is a turning process, and for relatively low strength material. So a low strength material, we're already in the 50 to 200 and something pounds. This is another turning example, and you can see, depending on which direction you're looking at the force, this is on the order of 300 pounds for a while. But when the tool starts to dull, this goes way up and goes to like 600 pounds. So this is mostly serving as a reminder to you that that when you do these calculations, you need to put in a factor of safety, because if somebody lets the tool become dull the tooling forces are going to go way, way up, and you cannot allow the part to come hurtling out of the fixture just because they did that, because somebody could get killed, or you can hurt a lot of, cause a lot of damage to machinery. And so we always need to apply a safety factor in the end. When we look at this also, you can see these are different depths of cut, and by doubling the depth of cut, it almost doubles the tangential force that's on the material. And so this is another reason that it's good to have a safety factor, especially if the cutting process is doing something like a casting, where because of loose tolerances on the casting itself, the depth of cut may vary pretty wildly from what you are planning on it being. Okay, so all that to say that we need to consider having a safety factor. All right. Also, some machining forces are really, really high. I looked up some different papers just to look at different numbers, and some of them are pretty surprising. So this is a big wing drilling jig. What they do is they put a wing skin, the wing is standing up against the wall, and this thing right here is a big drill that drills holes in it to hold the wing skin to the frame underneath. So I worked on a machine like this at Lockheed Martin for a while doing some data collection. Really cool machines, drill thousands and thousands of holes, but look at these numbers. There's a wing panel in one of these types of machines waiting to be drilled. Look at these numbers. If it is carbon fiber that you're drilling with a titanium subframe, the drilling force can easily be 29,000 to 58,000 pounds. Yeah, and you can tell that that's going to be true because look at the size of this, this part of the machine that is holding up the spindle. It has huge columns that are very, very thick. It has kickers going back. And so all of this quickly says to you, oh, they are dealing with some tremendous forces that are trying to have an overturning moment on that spindle. And so big, big forces. And this is not that big. This is a 1/4 inch diameter, 6 millimeter diameter. But they are going so fast through this material that they end up with these massive cutting forces. On the same machine with a different set of parameters, doing steel, hundreds to 200s of pounds. So the amount of force that you incur and deal with can vary greatly depending on what the machine is that you're doing and what the surface is. Because of that, you can't just assume a force. It's really important to calculate it. So in the next video, we'll talk about how to do that. I'll see you in the next video.